Do you know what ionizing radiation means? Why it's so important in many films such as Stowaway, and why is it considered as one of the main threats for future space travels by the NASA? Hello everybody, I'm Juan Manuel López, Aerospace engineering student and member of the 12th group of Material Science. In a few minutes, we are going to explain the main threats present into a 500 days interplanetary space flight due to ionizing radiation, and what would be the most suitable material to build an internal anti-radiation shield capable to keep safe against radiation in those zones where humans and more sensitive devices are going to be located. To perform this presentation, we are going to follow this index, starting by the kinds of existing radiation and its effects on materials, followed by the requirements that our material should have. Later, available materials are going to be mentioned to start with a deep and rigorous material comparison, from where a material will be chosen. To begin with, let's talk about the different kinds of ionizing radiation. Well, most known radiation particles are alpha and beta ones, but they will not be an important factor to take into account. Because of their small penetration power, a thin metal layer such as the thermal spacecraft shield can easily stop them. Gamma rays and neutron radiation are considered more harmful than other kinds of radiation. Because of its higher energy and its nature, they require a considerable thickness, highly dense material to provide enough protection, which could be an important factor to beat. Galactic cosmic radiation, or GCR, consists of a highly charged particle which usually contain HCE, or highly atomic number energy ions, or may produce them because of secondary radiation, once GCR first impact the aircraft shield. They are the worst of all because they are as small bullets which can break DNA molecules and kill human cells. To avoid big nuclei after secondary radiation, our chosen material should have relatively small atomic number. Solar cosmic rays are proton radiation which are originated in the sun. Its energy can be quite high, but with the proper shielding material, solar flares will not be a big problem to deal with compared with GCR. To finish with those radiation issues, it's important to consider that our material is not designed to spend big periods of time inside Van Allen belts, just to be able to cross them at least 4 times, through relatively low dangerous zones. Now let's move on and talk the effects that radiation has on material a long time. We differentiate atomic displacement because of the dissociation of chemical bonds due to the highly energy supply. There's also an electronic excitation, and finally a progressive diminution of mechanical properties and an acceleration of natural aging which will reduce the lifetime of our material. To provide analytical data, we need to follow several rigorous procedures which can analyze radiation parameters. One of the most powerful tools is bent block formula, but to simplify calculation we avoid this compressed formula to employ parameters such as the stopping power and the fragmentation cross-section. Stopping power represents how a material is able to stop a certain amount of particle energy over its thickness. Finally, fragmentation cross-section is also a good parameter when talking about how to diminish the dangerousness of an ionizing particle by terms of the required properties.
Once we have seen the types of radiation and their general effects, we are going to talk about the different groups of materials. Later, we will apply the parameters studied on these groups in order to filter them. Ceramics, despite of being one of the ancientest materials, started to be considered a few years ago. The discovery of their mechanical properties makes this material an ideal option for radiation shielding and engineering applications. Among these properties, we can find high strength, low thermal expansion, and good behavior against radiation. However, at high doses, some problems regarding cracking and thermal conductivity may appear. Graphites are one possible substitute because of the good heat treatment. At high doses, the changes of the properties are very similar to the ones of the ceramics, including an increase in hardness and strength. Finally, the drawbacks of the glasses are the increased density, the loss of transparency, and sometimes disintegration. According to hydrogenated compounds, they are, in theory, the best for radiation shielding the high atomic number energy ions. They are not useful for structural application, but some of them can be used for extra purposes, such as hydrogen storages or supply for astronauts in the case of water. Nanomaterials is another group that is currently being studied because of the wide range of morphological properties. Strength, low density, low atomic number, and neutron absorption are characteristics that can be found in boron nanotubes. Now we have to explain probably the most known choice for radiation shielding. The radiation of metal alloys causes a decrease in density and changes on the plasticity. One of the reasons why metal are used for spaceships, apart from the previous properties and an increase in hardness, is that in short periods of time there are no critical damages. Aluminium is one of the most used materials in this application. Nevertheless, there are disadvantages like the transition from brittle to ductile fracture and stress rupture. The last group is polymers. They experience effects from all the radiations. We can classify them in cross-linking, whose Young modulus, molecular weight and hardness increase, and chain scission, whose properties vary in the opposite way.
Nowadays, the most used is aluminum reinforced with polyethylene, but as it has large density and the effective dose reduction is low for our trip to Mars, new options have to be studied. We will choose among the materials presented earlier the following groups. Hydrates. We will know later that hydrogen makes the best option for radiation shielding, so that the best would be to manufacture solid hydrogen storages, and the search for a material would end up there. The problem is that it is not stable, and therefore what we will be looking for are components with high hydrogen concentration. Composites, because they have better mechanical properties than metals and they are multifunctional, which means that they can be used to shield and to be structural purposes as well, we will consider them as an option as well. Simulations and experiences have to be kept. As Granta doesn't support the database that we need for this experiment, we will use G12 and Monte Carlo for MATLAB. Simulations. They were carried with iron ions, which are the most difficult particles to shield against. The parameters that were taken into account were density, stopping power, and cross-section. Experience. For taking real values, we look for studies on the HIMAC, a particle accelerator in Japan, and the parameters taken into account in this case were the same, so that we could compare the two sets of data, but other physical parameters had to be taken into account, which are shown on the slide and presented into detail in the extended report. Discussing the results obtained. Well, regarding density, we notice in the graph that the bigger density of the material, the worse radiation shielding it makes. As an example, we observe aluminum as the worst case between the studied materials. Lithium borohydride, which counts with low density, is one of the best, and remember this one as it will be discussed later. In order to compare the radiation parameters, several groups were established. Group 1, low density hydrates, they are represented in blue. As hydrates have low density and high concentration of hydrogen, we can start thinking that they are going to be a better option, and there is even a way of making them better. By enriching lithium borohydride, we obtain a material that has more hydrogen and that can also be used as a fuel for taking off of Mars. Group 2, represented in purple. They are medium density hydrates. They are not interesting for our purpose because they have less hydrogen concentration and we don't want to look for that. Group 3, they are represented in red. They are the composites. They have less radiation shielding properties, but they can be used as structural materials, so we will consider them as a good option, as well in combination with the Group 1 hydrates. And Group 4, which is only aluminium represented in green, it is considered as the worst regarding radiation shielding parameters and density. So with this data and analysis that has been just provided, choosing a substitute range of materials should be easy.
At this point, we have to decide between the current material, aluminium polyethylene, and the possible substitute, lithium borohydride. On the one hand, the composite material combines the durability and strength of the metal with the flexibility provided by the polymer. It has a low melting point, but higher than the other one. In the advantages, we find the experience and excellent behavior against water and ultraviolet radiation. The price is also much smaller. However, it cannot be recycled. On the other hand, the lithium borohydride has a lower density and higher composition of hydrogen needed for the stopping power. Its performance includes corrosion resistance. The lack of knowledge about the material and the price are the main disadvantages. Well, we have analyzed the types of radiation and the effects on the materials, the parameters that we have used to do the selection, the current materials, and the possible substitutes. The aluminum polyethylene sandwich is the existing solution for the radiation shielding because of its good performance and the mechanical properties. We have seen that there are materials that act better under these conditions, but aluminium is used instead of them mainly thanks to the low price. The aim of this project was to find an internal anti-radiation shield without any structural application, and that is quite important. Now the price is not as relevant as before. Then the lithium borohydride is the best option for future radiation shielding. This hydrogen-enriched material presents the best behavior regarding to the stopping power and nuclear fragmentation. It is the ideal choice with a very low density and the highest effectiveness. Moreover, this actuation is also supported by numerous softwares. With all this given information, we hope that this material, the lithium borohydride, becomes habitual for radiation shielding of spaceships. Thank you very much for your attention.